Okay, so now that we've talked about exponential functions, and we've kind of talked about exponential functions and compared them to linear and quadratics, well, we're going to do that again, just a little bit more formal. So the idea is that when people in the real world, they gather information, they gather numerical data, and then they have to decide what kind of relationship would model their data. And they use that to help predict what may happen later on. In fact, there's a whole economics really looks at that, and they analyze data, and they kind of look at what's going to happen. They make predictions, and they use that using all this mathematical ideas that we have. And so that's what we're going to do. But we've only talked about linear, quadratic, and exponential stuff. And as you get farther along in math, you're going to see a lot more models that you could use. So linear, let's start with our linear, and I'm going to go ahead and highlight this so that way when I'm looking at my notes, it's really easy to find. Okay, so we are looking at linear relationships. And so the idea is if you were to graph your data, it's going to look like a line. So over here we see some data. We are graphing at 20 and 170, and then we graphed at 30 and 161.5. And so as we graph this, we see that it looks kind of like a straight line. So then we would say it's linear. Now, if we looked at it as a table, then we're going to start seeing that, oh, yep, as I go through these numbers, I see a constant difference. I'm adding 10 each time. And then I'm going to look for somewhat of a constant difference each time here. So it looks like I'm dropping down by about 9 or so, or 8.5. And that it seems similar. Now, it's not always going to be exact when you're working with real life data, but if you see a lot of those similarities, like that occurring, then you could say that it's linear. Now, once you know it's linear, how do you write a representation of that? So we have two different linear forms. We have slope-intercept form, where y equals mx, so m being our slope, plus b, which is our value on our y-axis, which we don't always have, so that's not always helpful. And then we have what we call transformational form, where we still have that slope or that change, but instead of starting at B, we now have a starting point HK. So this would be any point on our line, maybe our very first point that we would apply to that. And that's very similar to what we do with our quadratic formula, with our vertex form. So very similar. With a line, though, the power here is really 1, so it's an invisible one. With a quadratic, there's a 2. Okay, so quadratics, our next one. Quadratics, when they're graphed, they look like a parabola or a U shape. So as we can kind of tell here, we have kind of a U shape going on. If we look at connecting them, and this one's an upside down U shape. When we're looking at it as a table or a set, so really when we write it as a set, it looks like this. So here's my point 0.4, 10.44, that's a set. So when we write it as like ordered pairs. I like tables better because it just organizes information better, but you'll see them in both methods. For a quadratic, you're going to see that you're going to have common differences on the x's. So each one of these we're adding 0.2. And then what you're going to do is you're not going to see common differences for your y's. So if we were to look at this, hold on, I'm going to pause for a little bit while I calculate this. Okay, so now that I'm back, I've went ahead and calculated these differences. So here I'm adding 1.8. Here I'm adding 5.2. Here I'm subtracting 0.76. And here I'm subtracting 2.04. So then I'm looking at the differences here. So here now I'm subtracting 1.28. And then I'm subtracting 1.28. And so now I'm seeing how those common differences are occurring on the second round. So I look at that, and that's how I know it's a quadratic. And then we have our quadratic forms. So here's our quadratic equation, and then here's our vertex form, where we get kind of our center vertex point, and then we get that slope or pattern of change that occurs in a quadratic. Okay, exponential function. So when it's graphed, it looks like it's going to touch the x-axis on one end, but it never truly does. So this one looks like it is coming, looks like an exponential decay, so it's coming down and getting closer and closer to that x-axis, but it never really touches it. As a table, the x values have a common difference, so again, we're looking at common difference, but these have a common ratio, so it looks like each time I'm dividing by 2, which is really multiplying by 1/2. And so I get that common ratio. And so then we can write our exponential functions in one of these two forms, where like 1 would be your starting value, and this b is going to be that common ratio. So now what we're really doing is we're going to go ahead and graph information and kind of determine what is it going to look like. So we have a 0, 3, we have a 1, 0, we have a 2, -1, we have a 3, 0, and we have a 4, 3. So when we're looking at that, that looks like a genuine U shape, which is a quadratic. Okay, so now we move to the next one. We're going to go ahead and graph -4, -4, -3, -3.5. Okay, -2, -3, -1, -2.5, 0, -2, and 1, -1.5. Looks pretty consistent, looks pretty linear, so I would say this is a linear. So on our next one we have 0, 4, 0, 4, so that took care of that one. 1, 2, 2, 1, 3, 1/2, 4, 1/4. So again, typical exponential. And this one's going down, so I'm going to go ahead and give bonus points to myself here. It's an exponential decay. Okay, so that's what we could do for graphing it, which is nice, but sometimes our data is too hard to graph. We get really weird decimals or really big numbers. So then we could start looking at the patterns. So let's look at our x's. It looks like we're going up by 1 each time. So now let's look at our y's. Let's see, I'm going down 9, down 3, up 1, no, up 3, and then up 9. Okay, so now let's look at the differences here. So it looks like I'm adding 6, adding 6, adding 6. Okay, there's some common difference, so this would be a quadratic, because on our second set of differences, it's common. Okay, so let's look at our next one. Oh, was that it for that? Yep. So let's look at the next one. Let's see, common. We're good here. Okay, so now let's see what's happening here. We have adding 0, adding 2, adding 4, adding 4. That's not the same. Let's see. Oh, that's adding 6. Sorry. Adding 6. So let's see. We add 2. We add 2. Yep. Second differences are common, so this is a quadratic. Okay, so let's look at our next one. Let's see. Common. Yep. Yep. We're good here. Let's see. I add 0.25. I add 0.5. I add 1. I add 2. So let's see. This is 0.5. No, 0.25. 0.5. Add 1. I'm seeing the same pattern and over when I look at the second differences. So let's check then, and let's just erase this. And let's look at maybe there's a common ratio. So let's start down here. 1 times 2 gives us 2. 2 times 4 gives us 2. That looks good. So 0.25, yep, times by 2, times by 2. So we have a common ratio. So when I look at a common difference the first time, and I look at a common difference the second time, and it's the exact same, that means we're having a common ratio. So I went back, I determined that common ratio. This is exponential function. Now, for bonus points, since I'm timesing by 2 each time and my numbers are getting bigger, this is an exponential growth. Okay, so let's look at our next one. Let's see, common, we're good for the x's, it looks like. So let's see what's happening with the y's. Let's see, minus 3, minus 3, minus 3, minus 3. Yep, all of those are the same, so this is a linear. Okay, let's look at another problem. The data in the table shows the price of apples at a local store over several years. Which model best describes the data for apples? So let's look at what's happening here. We have add 0.45, add 0.45, add 0.45. Okay, so it looks linear based on the fact that I'm adding the same thing each time. Now, we're going to go ahead and write a function that models that. So let's think about what we did way back in like September, October in chapter 3. So we talked about linear functions, and we talked about slope. So slope is our change in y over our change in x. Well, how is our y changing? Our y is changing by adding 0.45. How is our x changing? Well, each time we add 1. So for my slope, it's going to be my change in y over my change in x. And now what I can do is I can find my initial starting value, or I can take any point on there. So I can go ahead and take my first point and plug it into that transformational form, kind of like our quadratic form. So this is going to be y equals my slope times x minus the x value of this point plus the y value of this point. And that could be my equation. Or I could go backwards and I can find a 0 value. So if I'm adding 0.45 this direction, I can work backwards and minus 0.45 to get a starting value of 0, which means now I can have y equals 0.45x plus my starting value of 0. And either way, it's really the exact same equation. It will give you the same answer each time. So now we could go ahead and predict, based on our pattern, the cost of apples in year 8. So if I used the red equation, I would do y equals 0.45 times 8, which will give us 3.6. So that is cost, so $3.60. Or I could use the Thiel formula, where y equals 0.45 times x minus 1, so 8 minus 1, and then add 0.45. A little bit more work, but it's an easier equation to write. So 0.45 times 7 gives me 3.15, and then I add 0.45, which gives me the same answer of $3.60. So what's nice is this was an easier equation to write, but a little bit more work to figure out the answer. This was a little bit more work to write the equation, but easier to calculate. So just an idea. Okay, so the data in the table shows the price of a game over several years. So let's go ahead and look at this. It looks like we've got constant change. Let's see, I'm adding $1. I'm adding $1.20. I'm adding let's see, 8.64 minus 7.2. $1.44. So let's see, is this different? I am adding 20. I'm adding 0.44. Okay, those differences, none of them are really the same. So let's go and see, maybe there's a number that we're timesing by each time. So let's figure out a possible R. I have no idea what I'm timesing by each time. So I'm going to take one value, I'm going to divide by its previous value. So 6 divided by 5 gives me 1.2. So let's check this. If I times by 1.2, 5 times 1.2 gives me 6. Now I'm going to times by 1.2, and I'm going to get 7.2. So here we go. We found our common ratio. Which model best describes? Well, this is exponential. Took us a little bit of work to find that, but it's exponential. Write the function that models the data for the game. So our starting value was $5. And then we are multiplying by 1.2 each time. And then this is going to be to the t power. Now why this? Why did I choose to use this? Because I started off at year 0 with 5. What if I wanted to use my starting value at 6 with 1? Well, this would be y equals $6 times 1.2, and then this would be t minus 1 because of this 1 right here. Well, what happens if I wanted to use this as a starting value? Well, if I use that as a starting value, then my equation would look like y equals 7.2, 1.2 times t minus 2 power. Because here's my starting value 2 years after, or on year 2. And all 3 of these functions will give us the same answer. So you're going to start seeing that I'm going to have a harder time grading stuff because there's going to be 4 different answers that give us the exact same thing. So now what we can do is we can go ahead and predict the cost of the game in year 7. So y equals 5 times 1.2 to the 7th power. So 1.2 to the 7th power times by 5. So this game will now cost $17.92. Or I could go ahead and do the teal version. So y equals 6 times 1.2 to the 7 minus 1 power. So 1.2 to the 6th power times by 6 gives me $17.92. And then I could go to the purple one if I wanted to, showing you that really all of these give us the exact same value. So 1.2 to the, let's see, 7 minus 2 is 5. So 1.2 to the 5th power times 7.2 gives us $17.92. So just several things for you to think about and work with on this.